tonight? Yes, you are. But I am going to give you points for it. So everybody's got your BFFs out. We got through the sine function, or no, through the logarithm function. We're ready to start with the sine function today. And so that's what we're doing. So remember, your responsibility at this moment is to know the name of the function, the equation of the function, and the shape of the function. Okay? So here we go. This word is said sine. And this word is said cosine. The equation for the sine curve is sin x. Now I know when you look at that, you think sin, but that is pronounced sine. So in this classroom, if you say sin x, I'm probably going to chuckle a little bit because that's goofy. That belongs in theology. This is sine. This is a sine curve. Now, the graph of the sine curve, I want you to put a dot at the origin. This is really important, and I'm going to count it wrong if you don't have this shape right. So you have a dot at the origin, then you're going to draw a hill, and then you're going to draw a valley. And then over here, you're going to do the same thing, only it's a valley and then a hill. So the curve goes hill, valley, but it goes right there through the origin. And this is a hill. Just to the right is a hill. Okay? That's what you have on your paper.
Cosin's opposite, right?
Now, in your reality, this goes up one and down one, but I know your grid is way too small. I mean, the things are really small. So you can have it going up higher, but label that 1 and this -1. Okay? Because these are 1 unit tall. Now, the cosine curve, which is COSX, cosine, that's called cosine. The cosine curve has the same shape, but here's the difference. You start with a dot right here, and there's your hill and valley, just like this.
Where do you start at? Like
right up here at 1. That's actually 1. That's up 1 and down 1, just like the sine curve. So do you see the hills and valleys are the same? If I took the axes out, which I'm going to put them back in because they're important, but if I took the axes out of both of my shapes, aren't they the same? They're just hills and valleys, that's all they are. The difference is how they are oriented. So when you are asked to sketch a sine curve, and later in the year, we're going to be sketching them much more detailed. But right now, the shape of a sine is this, the shape of a cosine is that. This point is important, and this point is important, because those are your reference points for the sine and cosine. Okay? All right? Okay, now that's sine and cosine. Okay, so now we're ready for the absolute value function. The graph of the absolute value, or the equation of the absolute value, is y equals absolute value x. That's the equation. The picture, anybody know what they look like? It is a V, Sam. Very good. It's a V. And you're going to remember that because absolute value is a V. Value V. Now, look back. Look at the squaring function. You don't want to get the absolute value confused with the squaring function. They have a lot in common, but these are straight. This is a sharp V. What is the squaring function? More of a U. Math teachers kind of cringe when we say U. It is a U if we're sticking with the letter thing, but it's called a parabola, right? That's what our squaring function is. All right, now we have my least favorite. My least favorite function is the greatest integer function. But I'm going to share it with you anyway, even though I don't care for it. There are a couple of ways you can denote the greatest integer. Some people use the brackets, and some people use the actual word int. It just sort of depends what book you're reading, who's writing it. I don't care which one you write down. You do, when there's multiples, guys, you don't have to write down all of them. You pick one you like. Which one's going to help you? So you're going to write this equation, or you're going to write this equation, okay? Then the shape of it. This is another really tricky one. I want you to put a nice solid dot right there at the origin. And I want you to go over an amount and put an open dot. And then I want you to step up from there, right above that open dot, put a closed dot. Go over and make another open dot. You see what I'm doing? I'm going to put a closed dot here. Go over. Now, all these bars you're drawing, technically they're 1 unit long. Now, they may be different on your grid, and I'm fine with that, but they should all be the same length. Every one of these steps is the same length, and they're down here too. So this goes on forever and ever, but we can't really put arrows on it, so we just have to understand that it goes on forever and ever. Last year, if you guys talked about these, you probably talked about them as step functions. They're just so weird. I don't care for them, but there's a practical application of them, so they are important. But that's your greatest integer function. Okay? And then the last one is our logistic function. And the logistic function has an equation that's a little bit weird. There's that E again. Remember the E? What other function did the E show up in? Exponential. This is the same E. This is the same E that we had in the exponential function. In its graph, okay, I need you to put an asymptote right here at y equals 0. And then I need you to come up however far you want to come up and put another asymptote, and that's going to be y equals 1. But don't just come up one block because there's just not enough room in there. So come up and just label it y equals 1.
Wait, what's the...
Okay, and then in between these two, you're going to put one of those squiggly lines that goes like this. So this thing approaches this asymptote. The farther we come to the left, the closer we get to 0, but the farther we go to the right, the closer we get to 1. And those, my friends, are your 12 BFFs. So here's what you're going to do over the weekend. You're going to get 12 note cards, or you're going to take a piece of paper and cut it up into 12 pieces. You're making flashcards. All right? So whatever material you use to do that, I couldn't care less. They do have to be physical flashcards. So I know you've got that thing on your iPad.
Can't use Quizlet?
No. I mean, you can to help you practice, but I want physical flashcards for me. So you're going to have 12 flashcards. On the front of the card is going to go the picture of the curve. Okay? So you're going to have a picture on the back, on the front. On the back of the card is going to go the name and the equation. Because we are going to be having quizzes where I might draw this picture and you have to tell me, oh, that's the logistic function. Or I might give you an equation and you have to tell me, oh, that's the greatest integer function. You have to start being able to match up the name, the equation, and the picture for these 12. Is that okay with everybody? All right. Now what we're going to do, though, is some exercises from your book. So we're in 1.3. For those of you that don't have a book, are just going to have to listen intently. Okay, so your notes, keep your BFF sheet out. Keep your BFF sheet out. You're going to use that for reference, because I doubt you have all this memorized at this point. It'd be great if you did. Some of you might. All right, here we go. So I am on page 113, and I'm looking at number 19. Number 19 says, look at your BFFs. I'm on page 113 of my textbook. Page 113, and I'm looking at number 19, problem 19, and it says, name the 4 functions that are odd.
Could we write on the...
You can write on the desk, you can do anything you want. These are actually in our notes though, so you might want to write the answers down in notes, I'm not sure. Now, what do we mean by odd functions? We mean they have symmetry about the origin. Now, what that means is, let me give you an example of one. Here's one of the answers. What curve is this one? That's the cubing function. That is an odd function because it has symmetry about the origin. What that means is, let's say this right here is the point 2, 8. Guess what point this is right here? If I fold it right across the origin, guess what point that is? -2, -8. If you are an odd function, then you're reflected across the origin. And what that means is, I don't have them for this curve, but if I had a point here that was -1, 4, what would be the across the origin point for that? 1, -4. So both signs change. If you're going from quadrant 1 to quadrant 3 across the origin, both signs change. Or 2 to 4, both signs change. These points don't have anything to do with this curve. All right, so that's one of them. Look at your other ones. Look at your notes, at your BFF sheet. Can you find 3 more functions that are symmetric about the origin? This is a little tricky, but see if you can do it.
I got one.
You got one? Which one do you have?
The reciprocal function.
Oh, the reciprocal function. Very good, Logan. That is indeed symmetric about the origin. If this is the point 1, 1, this is the point -1, -1. That is symmetric about the origin. Think about folding it. That's perfect. Can you find another one? Pat?
Absolute value.
Now, let's talk about that. Actually, the absolute value function is not symmetric about the origin, and here's why. If it's symmetric about the origin, everything in quadrant 1 is flipping exactly into quadrant 3. Well, there's nothing in quadrant 3. See here, look. Take Logan's function. If you took this and flipped it into quadrant 3, wouldn't it land right on top of itself? Yeah, that's not one. That one has symmetry, but not about the origin. We're going to talk about that one in a minute. The identity. There's another one, guys. Your identity function has symmetry about the origin. Because if you take quadrant 1 and fold it, doesn't it land right on top of itself? That's what symmetry means. It comes right back onto itself if you flip it across the origin. That's what odd means. O-O, odd origin. There's one more, it's a little tricky. What do you think, Logan?
Greatest integer function.
That one is so tricky. It's actually not, because the solid dots and open dots don't line up. They don't line up. You are exactly right. The concept is right. That one is a very tricky one. Yes, Mr. Brooker?
Sine or cosine?
Which one?
Ooh, I'm gonna go with sine.
That's a good guess. Sine is the one. Sine is odd because if I take, let's do one hill. If I take this hill and fold it into quadrant 3, doesn't it become that valley? Yeah. So the sine curve is the other one. So your 4 odd functions are the sine, the reciprocal, the identity. I didn't write the name down here. This is the identity. And the cubic function. Those are your odd ones. This is hard stuff, but you can figure it out. You can figure it out. All right, so then we're going on to number 20. The 6 functions that are increasing on their entire domain. So what that means is, any idea what increasing means? Going up. So when you draw it left to right, and that's the key, when you draw it left to right, your pencil does nothing but go up. So the sine function is not increasing on its entire domain, because as I draw it left to right, am I going up some of the time? But not all the time, right? I'm going up and down. So this one is not increasing on its entire domain. Are there any up here before I erase them that are? How about the identity? Is it increasing on its entire domain? That means when you draw the whole picture left to right, you're going up. Am I going up the whole time?
Yeah.
Yep. How about this one? Yeah, I'm curving a little bit, but I'm still going up the whole time, right? So here are 2 of them. What about this one? No, not increasing. Let's get rid of that one. All right, so I got 2, the identity and the cubic function.
Exponential.
Then you, oh, what?
The exponential.
Exponential. Remember what the exponential looks like.
It never ever ends.
Is my pencil going up the entire time I draw it left to right?
Yeah.
Yeah. What else? Pat?
Squaring.
Squaring function? Is the squaring function always going up as I draw it?
No.
What's my pencil doing?
Yeah, because it's negative place.
Huh?
But it's negative place, so it goes up.
I'm talking about my pencil, my
Oh.
physical pencil. Is my pencil rising? No. See, look at this one. Pat, look. See how my pencil's going up the whole time? That's what increasing means.
I got one.
Ooh, wait, so that's not that one.
I
Let's
got
get
one.
that
Square
one.
root.
Square root. That's the one that looks like this. Is my pencil going up the whole time? Yep. Logan?
The natural
The
logarithm.
logarithmic function. The logarithmic function. Okay, yeah, this is the log function. This is the square root function. How many have I got? 1, 2, 3. There must be one more. There's supposed to be one more.
With the logistic function work.
Let's look at the logistic function. Remember, it's the last one we did. It's got the 2 asymptotes and then this curve. Is my pencil going up the entire time I draw it?
It has to obey
I'm going left to right. Which direction is my pen going? Up, 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 up. Now, it slows down going up because it's running into this asymptote. But what does it do? Doesn't it constantly get closer?
Yep.
That means it's constantly going up, increasing. Okay? So increasing is a word we use when we talk about functions. And put very simply, increasing means your pencil is going up. When they say on its entire domain, they mean the whole way. Your pencil is going up the whole time. Good. All right, now we got 21. The 3 functions that are decreasing from negative infinity to 0. So when you graph it, when you set up your grid, this part of the curve, negative infinity to 0, your pencil is coming down. So can you find a function that is coming down on this side of the picture? Now, Pat.
Identity. Because it is going down on that side of the
Okay, no, the identity is not 1. I need to talk about this. When we test for increasing and decreasing, we are moving left to right. So when I am over here, Pat, moving left to right, which way is my pencil going? Up. That is not 1. I thought for sure, Pat, you were going to say the squaring function.
The absolute value.
Because what is happening as I go left to right, what is happening?
It's
Going down, right? What's the other one, PJ?
The
Absolute value, same thing. You're going to find that the squaring function and the absolute value function have almost everything in common. They said there's one more. Gabriella? The reciprocal function. Remember the reciprocal function. Now, I'm talking about this side. Which way is my pencil going? Down. She's exactly right. She's exactly right. The reciprocal function. There they are. Good job. Let's keep rolling. That was 21. Now we want 22. The 3 functions with infinitely many local extrema. Now, let's look at our squaring function. This right here is an extrema. It is a minimum point. Maximums and minimums are extrema. High points and low points. Okay? This curve does not have infinitely many. It has 1.
And so does the absolute value.
The absolute value has just 1. But we want, the problem says, the 3 functions with infinitely many extrema. Now, infinitely many extrema means infinitely many low points or high points. So look at your pictures. Which curves have infinitely many highs and lows? Maddie?
Squaring function?
The squaring function is right here, and it has 1 minimum. So it does have an extrema, but it doesn't have infinitely many. Cat?
Cubing function?
The cubing function doesn't have any extrema because when I draw it, it doesn't have any hills and valleys. Focus on hills and valleys, high points and low points. Izzy? Sine and cosine are the obvious ones. The third one is a little tricky, but the sine and cosine, what do they consist of, kids? Infinitely many hills and valleys. So if somebody said to me, Lisa, what is the maximum point on the sine curve? I would have to say there are infinitely many of them. This is a maximum, this is a maximum, this is a maximum, this is a minimum, 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 minimum. Infinitely many maxes and mins. Maximums and minimums together are called extrema. They're the extreme points. The tops of the mountains, the bottoms of the valleys. The other one is hard.
Would it be the greatest integer function?
It is indeed. It is indeed. The greatest integer function. Now, this function, this is the one I don't like, but here's the deal. If we look at just this part of the sine curve, that is a maximum, right? If we look at this part, that is the minimum. Those are called local maxes and mins. This is the highest point on that part of the curve. This is the lowest point on that part of the curve. Well, if you look at this, on this part of the curve, these are all the highest and lowest points. But what if you go to this part? Now, these are all the highest and lowest. Same thing here, same thing here, same thing here. The question said, how many, or find the curves that have infinitely many high and low points. Infinitely many, infinitely many, infinitely many. That's harder to see. Do you understand it here? That's the key. You get the concept here. That's a weird function, but that is the third one. Very good, Carter. The three functions with no zeros. Zeros, remember, are x-intercepts. So if I look at this graph, I have a 0 here, and here, and here, and here, and here, and here. If you want no zeros, that means what? Not crossing the x-axis. So, have you found some? The reciprocal function has no zeros. You are exactly right. That's your reciprocal function. Would everybody agree?
Yep.
No zeros. Carter.
Logistic function.
The logistic function. No zeros, because remember you got an asymptote there, right? No zeros. There should be one more. Pat?
Exponential?
The exponential function. No zeros, because it does this, right?
What function?
The square root function. Remember when I had you graph the square root function, I had you put a point right there? Where is that point? On the x-axis. That is a 0. That is a 0.
Wait, you said exponential, logistic, and what?
Exponential, logistic, reciprocal. Yeah, use your notes there. Your BFF sheet to help us. All right, the three functions whose range is all real numbers. The three functions whose range is all real numbers. Now, we talked a lot about domain. Domain is X. We haven't talked about range. You did last year. Range is Y. Y is up and down, okay? So if we want the range to be all real numbers, then we need our picture to go all the way down and all the way up without skipping anything. No skips. It's all the way down and all the way up without skipping anything. And there's supposed to be how many of them? 3. All right, can you think of 3 that go all the way down and all the way up? The identity. That is a perfect example. And the cubing. This is the cubing. Here's the identity. The range is all real numbers. You are exactly right.
Identity, cubing, and absolute.
Now wait, let's talk about the absolute value.
Hold on.
Does it go all the way up? Up, yes,
Not down.
but not down. So this is not all real numbers on the y's. We're looking at the y's. Going all the way up and all the way down. The logarithmic function is the third one. So we've got the identity, we've got the cube, and then we've got our logarithmic function as our third one that goes all the way up and all the way down. No one said reciprocal, and I'm glad, because usually somebody will say that. Does this one go all the way down? Yep. Does it go all the way up?
Yes.
But it has a skip in the middle. And if you're going to have a range that's all real numbers, you can't have any skips. And so this one doesn't have. That one doesn't have. These 3 right here. All the way down, all the way up, and no jumps, no skips. Okay, we're almost done with this. The 4 functions that do not have end behavior. Oh my gosh. When you found out you had to take Precal, this is exactly what you were scared of. This kind of notation. Right? Okay. So here's the deal. What this means is, here's my graph. As x approaches infinity. Now, these are positives. I don't normally write the positives on the positives, but I put negatives on the negatives. But as we're going to positive infinity, where does that happen on the graph? That's out here. This is x going to positive infinity. It's right here, right? So as you go right on the graph, as x goes to positive infinity, this is just another letter for y, right? Y also goes to positive infinity, which means as you go right, you are going up. So, where does it happen that as you go to the right, you also go up? Can you find a function where that happens?
Natural logarithmic function.
The logarithmic function. As we go to the right on this picture, is my pencil going up? Am I going right and up?
Yes.
Yes, indeed. So y equals log x is one of them. Very, very good. What's another one? The square root function. As we go to the right, my pencil is going up. The identity function. As we go to the right, my pencil is going up. How many of these are we supposed to have?
4.
4. Oh, we're missing one.
Ooh, exponential.
As we go to the right, the cubing is definitely one. And then we got the exponential. Why do I have, oh, read the question.
Does not.
Does not have that in behavior. So, well, let's go ahead and just continue our list. How many have we got?
5.
We got cubing already. Okay. So we've got. Did we get the identity? Yep. Okay. So we've got log. I've got it twice. All right. So I got log, square root, identity, and cubing, and exponential.
So these are ones that's yours.
Okay. So that's 1, 2, 3, 4, 5 of them. I need 6, 7, 8. I need 3 more. Because we're supposed to be finding the 4 that don't, but instead we're finding the 8 that do. How about this one? Yeah. Isn't my pencil going up? So the absolute value is going to go right along with it. It has the same kind of behavior. Very good, Toby. Very good. I think I got logarithm. Greatest integer. I hate that function, but I think you got it. Because the farther I go to the right, what is happening? I'm going up higher. So that's another one, greatest integer. So is that all of them? 1, 2, 3, 4, 5, 6, 7, 8. That's 8 of them.
Those are the ones that have.
So those are the ones that have this end behavior. So which, let's just make a list. What are the ones that I don't have up here? Got the sine and the cosine. Now stop a minute. Think about sine and cosine. As you go farther that way, you're just going up and down, right? You're not shooting up. You're going up and down. So that makes sense. What else? Reciprocal function. The reciprocal function, because as you go, as you go to the right, you're coming down. You're not shooting up into space. What's the other one? I'm missing one.
Logistic.
The logistic function. Because the logistic function, it goes up for sure. But does it go up to infinity? No, because it has a ceiling on it, right?
Yeah.
Okay. All right, so we didn't quite answer that question the way we were supposed to, but ultimately we did. One more. The 3 functions with end behavior as x approaches negative infinity as x approaches negative infinity, so which way are we going? Left. X is going to negative infinity. Y is going also to negative infinity. So there are three functions that when you go to the left, and I'm talking about all the way out here to the left, all the way out here, you're going down. Isn't that one of them right there? So one of them is the identity. This part right here is what we're talking about. As you go left, you're going down. What else? Exponential. Let's look at that one. I got a question about that one. Here's my exponential. Now, as I go this way, Toby, I am coming down. But am I going down all the way to infinity? No, because I have a floor that's stopping me. So if the question were, is it decreasing? The answer is yes. But it is not going to infinity. Like, see the difference? See how this is just shooting down into space? I need another curve that shoots down into space. That is not one. What else we got? Gabrielle? The cubing function? Absolutely. The cubing function shoots down into infinity. Yep. And the last one, PJ? The greatest integer function. As we go to the left, what is happening to, am I going up or down as I go this way? I'm going down. So there they are. There are the three. Okay? Now, do you see how your sheets were very helpful, right? But do you see how I was able to do that without a sheet? Because I know what the pictures look like. And that's...
Well, we need the flashcard.
I know. But well, yeah, a very long time. But what my point is, you need to get to that point. That's why we're doing the flashcards. So that you can be, so if I give a quiz question and I say, name a function, I don't think I'd probably say name all five or something, but name a function that is decreasing on its entire domain. You would think in your picture, or in your head, you'd be thinking about, okay, what pictures go down? When I draw them, what pictures only go down? So those are the kinds of questions I'll be asking. All right, that's good. We're done with that exercise though, perfect. So now we're gonna spend the rest of the period on page 10. Stop it, quit complaining. We're gonna spend the rest of the period. First of all, we have what, 11 minutes? You're not hearing my life story.
At least the last 3-4 minutes.
We'll see. We'll see. You guys act like you don't want to learn the math, and that's the most fun. I know you're fascinated by my life. It's so
We
exciting.
want to hear more about the nun who yelled at you.
Yeah.
And how
God
you
rest her soul. She's passed
how she
away.
mistook you for a student.
Yep. It's a true
When
story.
you thought you were going to fall off the freeway.
I don't think I told you that story. Someone's told you that story.
You did.
So that, did I tell you that?
No, I didn't hear about it.
You didn't tell us.
What happened?
That's what I'm for.
Oh my goodness.
All right. So here we go. We gotta get through these graphs.
Okay, let's
So how does the graph of the following compare to the basic function? And then I've set up a grid because I want you to actually graph it. So look on your sheet. What is the shape of the square root function? This is essentially a square root function. What is the shape of that? You should know that this is the shape of a square root function. Now, when you put a plus or a minus into the problem, this is important information. When you put a plus or a minus into the problem, that is going to take your shape and physically move it. It's called a translation, but what you're really doing is picking it up or down or left or right. okay? You must remember the rules. When the plus or minus is inside the function, and what I mean by that, this is not this. That would be a different problem. Do you see the difference? When the plus or minus is actually in the problem, in the square root, in the parentheses, when it is in there, inside, it's a horizontal shift. So you're going to be moving sideways. This problem is going to go sideways. This is like a parentheses. And remember what we've been, our pattern all throughout this has been, when you take a number out of the parentheses, it's the opposite. So instead of this being a -5, it's actually a +5. So you're going to take that picture and move it 1, 2, 3, 4, 5 to the right. So this is going to be the exact same shape as your square root function, but instead of being at the origin, it's moved 5 units to the right. Now, absolute value. Everybody should know now, look on your sheet, you know that's a V. Huh? But because there's a plus in there, we know we've moved up, down, right, or left. Now notice that this is not this. This is inside the function, and so would be horizontal. This would be a horizontal move. See where that one is?
Yes, so it should be 1
That's tacked onto the end. That's a vertical move. And a +1 is a +1. So that guy is going to go up 1 unit. You're going to have your very same shape, but it's going up 1 unit. We only do the opposite when it's X, when you're doing it inside the function. Okay? So now look at this one. Am I going in order? Is this the next one?
Yeah.
Okay. So everybody knows what that shape is. That's your exponential.
What is it,
Now-
0, 1?
That's, yep, 0, 1. That's that important point in the exponential. Now, look where the 1 is. I want you to see the difference between the 1 there and the 1 there. See how in one case it's actually built into the function, it's right part of the exponent, but here it's just tacked on the end. This one is just like this one. So when you have a number just tacked on the end, which way does that go? Up or down, up or down.
Up.
But a +1 is again going to go up. So you're going to take that picture and move it up 1. Okay, now wait a minute. Then where will that point be? 0, 2. And this was the asymptote, and that was at 0. So now the asymptote is up here at 1, because everything got shifted. And your shape, same shape, it's just lifted up 1 unit. You are absorbing a ton of material. I promise it's going to get easier as we do more of it, and we're going to do a lot of it. Okay, then we've got this one right here. All right, so what shape is that going to be, do you think?
Parabola.
It's got to be a parabola. Why is it a parabola? Because it's a version of squaring, right? So the normal squaring looks like this. Now, when you add 1, you can add 1 like that, or you can add 1 like this. There's different ways to add 1. Look where I added that 1. See how it's inside?
Yeah.
That's a horizontal.
So it should be
To the
left.
To the left, because we do the opposite when it's horizontal. So this guy is sitting at -1, 0 instead of at
1,
0, 0, which is where the original sat.
Yep.
All right, one more, and then I'll stop. I know. No, this is too fun. I want to keep going. All right, y equals x squared minus 1. All right, so first of all, what shape? Parabola. How do we know it's a parabola? It's a squaring. There's a minus 1. That's going to go up, down, left, or right. Look where the minus 1 is.
Vertical change.
Vertical change, minus is down. So you're going to have your parabola, but it is going to be down here at -1 because the normal one is at 0. And you dropped it down 1 unit. Okay? All right, I'll tell you quickly the road story. Are you sure I didn't already tell this?
No,
All right.
Izzy just knows it. Yeah, you